deep beneath the surface of our world, in chambers carved by water and time, a different kind of landscape unfolds. Here, where sunlight has never penetrated and silence reigns supreme, something extraordinary happens with a patience that makes glaciers seem hasty. Drop by drop, molecule by molecule, water performs an ancient alchemy, transforming dissolved minerals into structures of breathtaking beauty. These are the stalactites and stalagmites, the silent sculptures of the underground, and their story is one written in chemistry, geology, and the inexorable march of time. Picture yourself standing at the entrance of a limestone cave. The air temperature drops as you step inside, and that familiar surface warmth gives way to a cool, constant embrace that feels like stepping into another world entirely. Your eyes adjust to the dimness, and as your flashlight beam cuts through the darkness, it catches something that makes you pause. Hanging from the ceiling above, like frozen waterfalls or the teeth of some ancient stone beast, are formations that seem to defy simple explanation. They're stalactites, and they represent one of nature's most patient works of art. The silence in a cave is profound, almost tangible. It's not the silence of an empty room, but something deeper, more primordial. It's the silence of a place where time operates on a completely different scale than the world above. While we measure our lives in decades and our civilizations in centuries, these caves measure their transformations in millennia. A single stalactite hanging before you might have begun forming when the last ice age held the northern continents in its grip, when woolly mammoths walked the earth and humans were just beginning to paint on cave walls. But caves are not merely silent vaults of stone. Listen carefully, and you might hear it, the slow, irregular rhythm of water dripping, plink, a pause that might last seconds or minutes. Plink. Another drop falls. This is the heartbeat of the cave, the percussion section of an orchestra that has been playing since long before recorded history. Each drop carries within it the potential for transformation, bearing dissolved minerals from the world above into this realm of perpetual darkness. The beauty of these formations lies not just in their physical presence, but in what they represent. They are testament to the power of incremental change, to the profound transformations that can occur when tiny actions are repeated across vast spans of time. While a mountain can be thrust up by tectonic forces in geological instants, or worn down by wind and rain in millions of years, stalactites and stalagmites grow through a process so gradual that even the most patient human observer would struggle to perceive any change in their lifetime. Consider this. The average stalactite grows at a rate of about 0.13 millimeters per year. That's roughly the thickness of a sheet of paper. In a human lifetime of 80 years, a stalactite might grow just over 10 millimeters, barely half an inch. And yet, some of the stalactites you might see in a cave are dozens of feet long, representing hundreds of thousands of years of continuous growth. In caves like Gaping Gill in England, some stalactites in the fossil passages have been dated to at least 350,000 years old. These formations were already ancient when our species, Homo sapiens, first emerged in Africa. The formations you see in caves today are not static monuments, frozen in time like fossils. They are living processes, still growing, still changing, still being shaped by that same patient drip of water that began their formation eons ago. In caves that remain active, where water still seeps through the limestone above and drips into the chambers below, new layers are being added, even as you read these words. The process that created the formations we see today continues, following the same chemical pathways, obeying the same physical laws, building tomorrow's wonders atom by atom, molecule by molecule, drop by drop. The ancient Greeks and Romans knew about these formations. Pliny the Elder, the Roman natural historian, wrote about them in his Natural History, describing how water could create stone through its dripping. But for thousands of years, caves were places of mystery and often fear. Many cultures believed caves to be entrances to the underworld, portals to realms of spirits and demons. It wasn't until relatively recently, in geological terms just yesterday, that humans began to explore caves systematically and to understand the processes that created their wonders. Even now, with all our scientific knowledge, standing in a cave surrounded by these formations can feel like stepping into a cathedral built by forces beyond human comprehension. The formations themselves seem almost alive in their variety. Some stalactites are thin and delicate, like stone straws hanging from the ceiling, so fragile that a touch could break them. Others are massive, bulbous structures that seem to flow like frozen honey from ceiling to floor. Stalagmites rise from the cave floor in equally diverse forms, some tall and slender like stone candles, others squat and wide like melted wax, still others taking on shapes that early cave explorers compared to everything from Buddhist statues to coffee pots, from swords to tongues to carrots, limited only by the imagination of the observer. Colors add another dimension to this underground art gallery. While many formations are white or cream-colored, the pure hue of calcium carbonate, others display a stunning array of colors. Red and orange formations speak of iron oxide carried in the water, painting the stone with rust's warm palette. Brown and tan hues tell of organic material from the soil above, the decomposed remains of plants and the humus that feeds the forests on the surface. In rare cases, you might see green or blue formations, colored by copper minerals, or even black formations where manganese has left its mark. Each color is a chapter in the story of what lies above the cave, a chemical signature of the rock and soil the water passed through on its journey from surface to ceiling. The play of light in caves transforms these formations into something even more spectacular. In the natural darkness of the cave, a single light source creates dramatic shadows and highlights, making the formations seem to shift and move as you pass. The reflective quality of wet calcite means that formations can seem to glow when illuminated, as if lit from within. Some formations contain trace amounts of uranium, which makes them fluoresce under ultraviolet light, creating an otherworldly display of ghostly colors in what would otherwise be complete darkness. To understand how stalactites and stalagmites form, we need to follow water on a journey that begins in the sky and ends in the patient construction of stone. It's a journey governed by chemistry, a process where simple molecules combine and recombine in ways that transform liquid into solid, creating structure from solution. The story begins with rain. As water droplets form in the atmosphere, they begin absorbing carbon dioxide, the same gas that we exhale with every breath, the same gas that plants need for photosynthesis, the same gas that has become so prominent in discussions of climate change. When carbon dioxide dissolves in water, it forms carbonic acid, weak acid, but an acid nonetheless. The chemical formula tells the story. Water, which we represent as H2O, combines with carbon dioxide, CO2, to form carbonic acid, H2CO3. This is the same process that makes rainwater naturally slightly acidic, with a pH typically around 5.6. But the rain's journey as a carbonic acid solution is just beginning. As it falls to earth and soaks into the ground, it passes through layers of soil, and here something crucial happens. Soil is not just dirt, it's a living, breathing ecosystem, teeming with bacteria, fungi, plant roots, and decomposing organic matter. All of these organisms respire, taking in oxygen and releasing carbon dioxide, just as we do. The soil air, the mixture of gases that fills the spaces between soil particles, can contain 10 to 100 times more carbon dioxide than the atmosphere above. As water percolates through this soil, it absorbs more and more carbon dioxide, becoming increasingly acidic. This acidified water, now a more concentrated solution of carbonic acid, continues its downward journey, and eventually it reaches the bedrock below the soil. In many places, this bedrock is limestone, a sedimentary rock composed primarily of calcium carbonate, the mineral calcite. And here is where the real magic begins. Carbonic acid, though weak, is perfectly suited to dissolve calcium carbonate. The chemical reaction is elegant in its simplicity. The acid breaks down the calcium carbonate, converting it into calcium bicarbonate, which, unlike its parent compound, is highly soluble in water. The equation looks like this. Calcium carbonate, KCO3, reacts with carbonic acid, H2CO3, to form calcium bicarbonate, CaHCO3.2. This calcium bicarbonate remains dissolved in the water, invisible to the eye. But it's this dissolved mineral that will eventually become the building block of stalactites and stalagmites. Now imagine this water, laden with dissolved calcium bicarbonate, continuing its downward journey through tiny cracks and fissures in the limestone. These pathways through the rock are not uniform. Some are wider, allowing water to flow more freely. Others are narrow, forcing the water through spaces so tight that its movement is measured not in liters per second, but in individual drops per hour. The water follows the path of least resistance, gradually dissolving more limestone as it goes, slowly enlarging the very passages it travels through. Eventually, after a journey that might take months or even years, the water reaches an open space, a cave chamber. The cave atmosphere is different from the water-saturated world the water has been traveling through. In the open air of the cave, something can happen that couldn't happen in the confined spaces of rock. Carbon dioxide can escape from the water into the air. This process, called degassing, is similar to what happens when you open a bottle of carbonated soda. The carbon dioxide that had been dissolved under pressure is released when the pressure is reduced. As carbon dioxide escapes from the water drop hanging on the cave ceiling, the chemical equation that created calcium bicarbonate begins to reverse. Without enough carbonic acid to keep the calcium carbonate in solution, it precipitates out, returning to its solid form. This is the key to everything. Calcium bicarbonate, CaHCO3.2, converts back to calcium carbonate, KaCO3, plus water, H2O, plus carbon dioxide, CO2. The carbon dioxide escapes into the cave air. The water evaporates or falls to the floor below. And the calcium carbonate stays behind, a tiny deposit of solid mineral on the cave ceiling. This is how stalactites begin, with a single drop of water and the infinitesimally thin layer of calcite it leaves behind. The beauty of the process is that it's self-perpetuating. As long as water continues to seep through the rock above and drip into the cave, as long as that water is carrying dissolved calcium carbonate, the formation will continue to grow. Each drop adds its contribution, a microscopic layer that joins all the layers that came before. The rate at which this happens depends on several factors, all intricately connected. The drip rate is crucial. If water drips too quickly, there isn't enough time for the carbon dioxide to fully degas from each drop before the next drop forms. The water essentially carries most of its dissolved calcium carbonate with it when it falls to the floor below. In this case, you'll get faster stalagmite growth and slower stalactite growth, or even no stalactite at all. just a wet spot on the ceiling. But if the drip rate is slow, allowing several minutes or even longer between drops, something wonderful happens. The water in each drop has time to lose its carbon dioxide to the cave air. As it does so, calcium carbonate precipitates out, not just on the ceiling where the drop hangs, but actually on the surface of the drop itself. If you could look closely at a drop hanging from a forming stalactite, you might see tiny crystals of calcite forming on its surface, like ice crystals forming on a winter pond, but made of stone instead of frozen water. The chemistry is also affected by the concentration of calcium carbonate in the water. Water that has had a longer journey through limestone, or that has traveled through regions where the limestone is more pure or more readily dissolved, will carry more calcium carbonate in solution. This means more material available to precipitate out and potentially faster growth rates. The most rapidly growing stalactites, forming under ideal conditions, with highly mineralized water and slow, steady drip rates, can grow at rates up to 3 millimeters per year. That's still less than 1/8 of an inch annually, but it's fast by cave formation standards. Temperature plays a role too. Calcium carbonate is more soluble in cold water than in warm water. This might seem counterintuitive, as we often think of hot water as a better solvent, but it's one of the quirks of calcium carbonate chemistry. This means that as water warms slightly when it enters the cave from colder passages above, it becomes less able to hold calcium carbonate in solution, encouraging precipitation. Cave temperature is typically very stable, usually matching the average annual temperature of the region above. This stability is part of what makes caves such excellent climate archives, but we'll explore that more later. The pH of the water, its acidity or alkalinity, is another crucial factor. For stalactites and stalagmites to form, the water needs to be close to neutral or slightly alkaline by the time it reaches the cave. If it's still too acidic, it will continue to dissolve limestone rather than depositing it. The ideal pH range is typically between 7.5 and 8.5. This pH range allows for what geochemists call supersaturation. The water holds more dissolved calcium carbonate than it normally could, and this supersaturation drives the precipitation process. In some caves, especially those in cold regions, the chemistry can be further complicated by the precipitation of amorphous calcium carbonate before it converts to crystalline calcite. This amorphous form, discovered in cave environments relatively recently through advanced microscopic techniques, is less stable than calcite and eventually converts to the crystalline form. However, during this conversion, some of the geochemical signals that the formation has recorded can be altered, adding another layer of complexity to the study of these formations. The type of crystal that forms also matters. While calcite is the most common mineral in cave formations, aragonite, another form of calcium carbonate with a different crystal structure, can also form under certain conditions. Aragonite tends to form when the magnesium content in the water is high, or when the temperature is higher. It creates formations that are often more delicate and intricate than calcite formations. Aragonite is also useful for dating, as it can be dated very precisely using radiometric methods, though it's less stable than calcite and more prone to converting back to calcite over very long time periods. Let's follow the birth and growth of a single stalactite, from its inception as a barely visible ring of calcite to its potential destiny as a massive stone formation hanging many feet from a cave ceiling. It begins, as all stalactites do, with a single drop of mineral-laden water clinging to the cave ceiling. The drop hangs there, suspended by surface tension, that remarkable property of water that allows it to form cohesive drops, rather than simply spreading out as a thin film. The drop is in no hurry. It might hang there for minutes, perhaps even hours, slowly losing volume to evaporation, but more importantly, slowly losing carbon dioxide to the cave air. As the carbon dioxide escapes, calcium carbonate begins to precipitate. Remarkably, this precipitation doesn't happen uniformly across the entire drop. Instead, it happens primarily at the very rim of the drop, at the point where the water is clinging to the ceiling. This is where surface tension is highest, and it's also where the most efficient degassing occurs. The result is that the first calcium carbonate deposited forms a ring, a tiny circular band of calcite adhering to the cave ceiling. When this first drop finally falls, perhaps dislodged by the formation of the next drop pressing up behind it, it leaves behind that ring of calcite, so thin as to be nearly invisible. But this ring is the foundation, the cornerstone of everything that follows. The next drop of water doesn't hang from smooth limestone anymore. It hangs from that ring of calcite. And when it deposits its calcium carbonate, it adds to the ring, building it up higher, making it slightly thicker, slightly longer. Drop after drop repeats this process. The ring grows downward, extending away from the ceiling. But here's what's crucial, because the precipitation happens at the rim of the drop, and because each drop hangs from the bottom of the growing formation, rather than spreading across its surface, the formation grows as a hollow tube. This is the famous soda straw stalactite, and it's one of the most delicate and beautiful formations in the cave world. Soda straw stalactites are typically about 4 to 5 millimeters in diameter, roughly the width of a drinking straw, hence the name. They're hollow through their entire length, with a central channel just wide enough for a single drop of water to pass through. They can grow remarkably long under the right conditions. Some soda straws have been found that extend more than 2 feet from the ceiling, though they're incredibly fragile. A touch can break them. Even a strong air current in the cave can cause them to vibrate and potentially snap. The thinness of a soda straw's walls is astonishing. In some cases, the wall might be less than a millimeter thick, translucent when backlit, looking more like glass than stone. Growing at the typical rate of a fraction of a millimeter per year, a 2-foot soda straw might be several thousand years old, and yet it could be shattered by a careless gesture or destroyed by a single moment of thoughtlessness. But soda straws, while beautiful, are not the destiny of most stalactites. Eventually, something happens to most of them that changes their character entirely. The narrow central channel, that tube through which water has been traveling, becomes blocked. This can happen in several ways. A piece of debris, perhaps a tiny fragment of clay or organic matter from the soil above, might lodge in the tube. Calcium carbonate might precipitate inside the channel rather than just at the rim, gradually narrowing the passage until it closes completely. Or a particularly large volume of water might overwhelm the formation, depositing calcium carbonate not just at the growing tip, but along the sides as well. Whatever the cause, once the central channel is blocked, water can no longer drip neatly through the formation's center. Instead, it must flow over the outside of the stalactite. This changes everything. Now, as the water trickles down the exterior surface of the formation, it can deposit calcium carbonate along the entire length, not just at the tip. The stalactite begins to thicken, to grow outward as well as downward. This is how the characteristic cone shape of most stalactites develops. They're thickest at the top, where they attach to the ceiling, and they taper gradually to a point at the bottom, This shape is purely a function of where the water flows. More water flows over the upper portions of the stalactite, so more calcium carbonate is deposited there. As the water trickles downward, some evaporates, some drips off, and the film of water becomes thinner and thinner. By the time it reaches the tip, there's very little water left, so very little deposition occurs there. The rate at which a stalactite thickens depends on how much water flows over its surface. In a very wet cave with abundant water seepage, a stalactite might thicken relatively quickly, becoming wide and bulbous. In a drier cave or during drought periods, the stalactite might remain slender and graceful. Some stalactites show clear evidence of changing growth patterns over time. A slender lower section might give way to a bulbous middle, then taper again near the top, each section recording a different climatic period in the cave's history. The surface texture of stalactites can vary enormously. Some are smooth and glossy, as if polished, the individual layers of calcite so thin and uniform that they create an almost glass-like surface. These form in very stable conditions, with steady, unchanging drip rates and constant water chemistry. Others are rough and irregular, covered with bumps and ridges. These might form in more variable conditions or in places where the water flow patterns change frequently. Some stalactites develop what cavers call drip curtains or shields, thin, sheet-like extensions that hang from the main body of the formation, like flags or banners. These form when water flows down a sloped surface of the ceiling, rather than dripping vertically. The water follows the slope, creating a thin, vertical sheet of flowing water, rather than individual drops. As calcium carbonate precipitates from this sheet, it creates a curtain-like formation, often displaying beautiful translucent bands when backlit. Colors in stalactites tell stories of what's in the water and in the rock above. Pure calcium carbonate produces white or cream-colored formations, but pure conditions are rare in nature. Iron oxide, rust essentially, creates yellow, orange, and red stalactites. These warm colors are common in areas where the limestone contains iron-rich layers, or where the water has passed through iron-bearing soils. The intensity of the color depends on the concentration of iron. A light tinge might create a pale yellow, while high concentrations produce deep oranges or even brick reds. Organic matter from decomposing vegetation in the soil above can create brown or tan colors, and in some cases, nearly black formations. These dark-colored stalactites are particularly common in caves beneath forests, where the soil is rich in humus. Manganese oxide can also create dark brown to black colorations. In rare cases, stalactites can be green or blue, colored by copper minerals from the rock above, or white with blue tinges from moon milk. A paste-like cave deposit rich in certain bacteria. Many stalactites show bands of different colors, layer upon layer, like the rings of a tree. These bands are annual records of changing conditions. A white band might represent a dry year, when clear, filtered water with little organic content seeped through the rock. A brown band might mark a wet year, when heavy rainfall washed more organic matter into the groundwater. Reading these bands is like reading the pages of a history book, though the language is written in minerals rather than words. The growth of stalactites is not always steady and uninterrupted. Periods of growth can be separated by periods of hiatus, times when no water dripped and no calcium carbonate was deposited. These hiatuses might be caused by changes in the water table, by the development of new drainage patterns in the rock above, or by long-term climate changes that altered rainfall patterns. In some cases, stalactites have been found with growth hiatuses lasting thousands of years. visible as clear demarcation lines in the formation's structure. Some stalactites show evidence of having been partially dissolved after they formed. This happens when the chemistry of the cave changes, when the water becomes acidic enough to dissolve calcite rather than deposit it. You might see stalactites with rough, pitted surfaces, or with areas where layers have been eaten away. This is particularly common in caves near the water table, where the cave can become flooded, submerging formations in acidic water for extended periods. Perhaps one of the most fascinating aspects of stalactites is their internal structure. If you could slice through a stalactite from top to bottom and examine the cross-section under a microscope, you would see an intricate architecture of crystals. The calcium carbonate doesn't precipitate randomly. It forms organized crystal structures, with the crystals oriented perpendicular to the growing surface. These crystals are typically elongated, needle-like, or columnar, and they grow outward from the center of the formation. Under polarized light, these crystals become even more spectacular, displaying vivid colors based on their orientation and thickness. Geologists studying stalactites use these crystal patterns to understand growth conditions. Changes in crystal size or orientation can indicate changes in drip rate, water chemistry, or temperature. The study of these microscopic features is called speleothem microfabric analysis, and it's revealed an astonishing level of detail about past conditions in caves. While stalactites capture our attention by hanging dramatically from cave ceilings, their counterparts rising from the floor below are equally remarkable, though they form through a slightly different process. Let's now turn our attention downward to the stalagmites. Remember that drop of water that fell from the tip of the stalactite. Its journey isn't over. As it falls through the cave air, it still carries some dissolved calcium carbonate that didn't precipitate on the ceiling. When this drop hits the cave floor, the impact is dramatic on a microscopic scale. The drop splashes, spreading out in all directions, and in that moment of impact, several things happen simultaneously. First, the physical shock of impact can trigger additional degassing of carbon dioxide. The drop suddenly exposes a much larger surface area to the cave air as it spreads out, allowing more rapid loss of carbon dioxide. Second, some of the water is thrown off in tiny droplets by the splash, but these droplets are so small that they evaporate almost immediately in the cave air, leaving their dissolved calcium carbonate behind. Third, the remaining water begins to spread out as a thin film on the cave floor. All of these factors contribute to the precipitation of calcium carbonate, but unlike the process on the ceiling, this precipitation doesn't happen in a neat ring. Instead, it happens across a broader area, wherever the water from the splash lands. This is why stalagmites never form as hollow tubes like soda straws. From their very first moment of existence, they're solid formations, built up layer by layer from their base. The first visible sign of a forming stalagmite might be nothing more than a small mound or bump on the cave floor, perhaps a few millimeters high, roughly circular. This is where most of the water from the drips has been landing, where most of the calcium carbonate has been precipitating. Unlike a stalactite, which starts small and grows larger, a stalagmite often starts with a broad base and grows upward. The shape of a stalagmite is largely determined by how the water spreads when it hits the forming structure. In cases where water drips very slowly, each drop has time to spread out significantly before the next drop arrives. The water flows down the sides of the growing stalagmite, depositing calcium carbonate as it goes, and the result is a broad, flat top formation that might look like a mushroom or a stumpy cylinder. Cave explorers have compared these formations to toadstools, drums, and even bathtubs, when they develop a depression in the center from the constant impact of dripping water. But when water drips more rapidly, something different happens. Each new drop arrives before the previous drop has had time to spread out much. The water tends to stay more localized at the point of impact, and calcium carbonate is deposited primarily in the center of the formation rather than spreading widely over its surface. This produces what cavers call broomstick stalagmites, tall, slender formations that rise like stone candles from the cave floor. These can be remarkably thin relative to their height, sometimes only a few inches in diameter, but several feet tall. The fastest growing stalagmites occur in conditions where there's a balance, enough water to provide abundant calcium carbonate, but with drip rates slow enough to allow proper degassing and precipitation. These formations can grow several millimeters per year under ideal conditions, though this is still considered rapid only in the geological sense of the word. A stalagmite growing at this rapid rate would still take over 3,000 years to reach 10 feet in height. One of the most remarkable aspects of stalagmites is their internal structure. Because they build up layer by layer, with each drop adding its contribution on top of all the drops that came before, stalagmites preserve an incredibly detailed record of their growth. If you cut a stalagmite in half vertically, from top to bottom, you can see these layers, sometimes thousands of them, stacked like the pages of a book. Each layer represents a distinct period of deposition. In some stalagmites, these layers are visible to the naked eye, appearing as bands of slightly different colors or textures. In others, the layers are microscopic, visible only under magnification. But whether visible or invisible, they're there, and they can be counted and analyzed. Each one a snapshot of the conditions under which it formed. The layers in a stalagmite are incredibly thin. In some slow-growing formations, individual layers might be only a few micrometers thick, thinner than a human hair. A single millimeter of stalagmite growth might contain dozens or even hundreds of these microlayers, each one the product of a single drip or a short period of dripping. This level of detail is what makes stalagmites such valuable climate archives, which we'll explore more deeply later. The crystal structure within stalagmites is fascinating. The calcite crystals don't grow randomly. They orient themselves perpendicular to the growing surface, standing upright like tiny pillars. As the stalagmite grows taller, these crystal pillars extend upward, maintaining their orientation. This creates a radial pattern when viewed in cross-section, with crystals radiating upward and outward from the center of the formation. Not all stalagmites are simple pillars. Some develop bizarre and wonderful shapes. Stalagmites can be twisted and curved, spiraling as they grow. This can happen for several reasons. If the drip point above moves slightly over time, perhaps because the stalactite feeding it shifts, or because the water finds a new path through the rock, the stalagmite below will grow toward the new drip point, creating a lean or curve. Air currents in the cave can also deflect falling water droplets, causing the impact point to shift gradually over time. Some stalagmites develop terraces, step levels that give them the appearance of miniature pagodas or wedding cakes. These form when the drip rate varies significantly over time. During periods of rapid dripping, water splashes outward more forcefully, depositing calcium carbonate over a wider area and building out a terrace. When the drip rate slows, growth becomes more concentrated in the center again, starting a new upward growing segment on top of the terrace. One particularly interesting type of stalagmite formation is what geologists call a speleothem. These form in areas where water doesn't drip in a steady rhythm, but instead falls in splashes or spurts, perhaps from a pool that occasionally overflows. or from a passage that drains only during heavy rainfall. The calcium carbonate deposits in irregular patterns, creating lumpy, knobby formations that look like they were splattered in place, hence the name. The color of stalagmites follows the same patterns as stalactites, with white being the color of pure calcium carbonate, and various impurities creating the spectrum of yellows, oranges, reds, browns, and occasional greens or blues. But in stalagmites, there's an added factor. The color can also be influenced by organic material that accumulates on the cave floor. Bat guano, for instance, can add distinctive brown or black coloration to stalagmites growing near bat roosts. Ancient human activity in caves can also leave traces. Stalagmites that grew over old fire pits might incorporate charcoal particles, giving them a dark, sooty appearance. Some of the most spectacular stalagmites in the world have acquired names from their resemblance to familiar objects. In Ingleborough Cave in England, one of the most famous formations is called the Buddha, a stalagmite whose shape, with a wide base and narrower top, supposedly resembles a seated figure in meditation. In the same cave, another formation is called the coffee pot, for its uncanny resemblance to a traditional coffee kettle. The Skittles, a group of stalagmites in the same cave system, are so named because they look like bowling pins standing in a row. These anthropomorphic names reflect our human tendency to find familiar shapes in natural formations, but they also speak to the incredible diversity of forms that stalagmites can take. No two stalagmites are exactly alike. Each one is a unique sculpture created by the specific conditions under which it formed. The water chemistry, the drip rate, the cave temperature, the presence or absence of air currents, even the slope of the floor beneath the formation. All of these factors combine to create each stalagmite's individual character. One crucial difference between stalactites and stalagmites is their relative robustness. While stalactites, especially soda straws, are incredibly delicate, stalagmites tend to be much sturdier. Growing upward from a solid foundation, with their mass distributed through a relatively wide base, they can withstand forces that would shatter their hanging counterparts. This greater durability is one reason why stalagmites are often better preserved in caves than stalactites, and why they're the preferred choice for scientists collecting samples for climate studies. But this doesn't mean stalagmites are indestructible. They're still made of calcium carbonate, a relatively soft mineral that can be scratched with a fingernail, and they can be damaged by impact, by acidic water, or by human contact. The oils from human skin, transferred to the surface of a stalagmite by a thoughtless touch, can alter the surface tension where water clings to the formation, disrupting the deposition pattern and potentially stopping growth at that spot entirely. This is why responsible cave conservation emphasizes the critical importance of not touching formations. In caves where conditions remain stable for extraordinarily long periods, where water continues to drip in the same place for millennia upon millennia, something remarkable can happen. A stalactite and its companion stalagmite can meet. When this occurs, when stone hanging from above joins with stone rising from below, a new formation is created, a column, also called a pillar. The process of column formation is elegant in its simplicity, but remarkable in its requirements. Remember that stalactites grow downward at a rate of perhaps a fraction of a millimeter to a few millimeters per year, while stalagmites grow upward at similar rates. For them to meet, both must continue growing for tens of thousands, or even hundreds of thousands of years without interruption. And critically, the drip point above must remain stable throughout this entire period. Imagine the conditions required. The crack in the rock through which water seeps must not become blocked. The water table must not shift dramatically. The climate above must not change so drastically that rainfall patterns are completely altered. The cave itself must remain stable, not collapsing or significantly changing shape. When you consider all these requirements, the existence of columns becomes even more impressive. They're monuments not just to time itself, but to stability, to unchanging conditions persisting across epochs. The moment of contact between stalactite and stalagmite is, in geological terms, unremarkable. There's no dramatic joining, no visible seam in most cases. As the two formations grow closer, the gap between them narrows from feet to inches to millimeters. The water dripping from the stalactite lands on the stalagmite below, and for a while, both continue growing independently. But eventually, the stalagmite grows tall enough that the water dripping from the stalactite no longer falls freely, but instead flows directly onto the top of the stalagmite. At this point, calcium carbonate begins depositing in the gap between them. The water flows down from the tip of the stalactite, across the increasingly narrow gap, and onto the top of the stalagmite. Calcite precipitates throughout this path, and the gap closes. What was two formations becomes one continuous structure connecting floor to ceiling. Once a column forms, its growth pattern changes. Water now flows down the entire length of the formation, from ceiling to floor, and calcium carbonate can be deposited anywhere along this path. Columns often become quite thick over time, sometimes growing to tremendous proportions. Some columns are more than 6 feet in diameter and over 60 feet tall, massive pillars of stone that can resemble the columns of ancient temples or the trunks of enormous trees. The shape of columns can vary considerably. Some are relatively uniform in diameter from top to bottom, suggesting that growth rates were similar for the stalactite and stalagmite phases. Others show a distinct bulge in the middle, where the original stalagmite and stalactite were thickest before they joined. Still others taper at top and bottom, thick in the middle, having grown outward most rapidly at the junction point where the two formations originally met. The surface of columns can be smooth or elaborately decorated. Water flowing down a column can create flowstone, thin sheets of calcite that drape the column like a coating. In some cases, new stalactites begin growing from the sides of a column, fed by water that seeps through the rock and emerges on the column's surface. These secondary stalactites can create fantastically complex structures, with columns sprouting arrays of smaller formations like branches from a trunk. Columns are often aligned along cave ceilings, following natural joints or fractures in the rock above. Where there's a joint, there's often greater water penetration, and so you might see a row of columns marching across a cave chamber, each one following the same crack in the ceiling. This linear arrangement can create the impression of a colonnade, a row of pillars supporting some vast underground temple. But columns are not the only formations created by the meeting of cave floor and ceiling. Other types of formations can grow between these surfaces, each with its own character and formation process. Flowstone, for instance, can create what look like frozen waterfalls cascading from ceiling to floor. This forms when water flows down a cave wall or over a sloped surface rather than dripping freely, depositing calcium carbonate in thin sheets as it flows. Flowstone often displays beautiful banding, with alternating layers of different colors or textures visible in cross-section. These bands can represent seasonal variations, with different colored layers forming in wet and dry seasons. Or they can represent longer-term changes in water chemistry or flow patterns. Some flowstone formations are translucent, allowing light to penetrate their surface layers, creating an ethereal glow when illuminated. Draperies or curtains are another formation type that can connect ceiling and floor. These form when water flows down a sloped ceiling, following the line of greatest slope. As the water flows, it deposits calcium carbonate along its path, building up a thin, vertical sheet of stone. Draperies can be remarkably thin, in some cases less than a centimeter thick, and they often display translucent bands visible when backlit. The bands in draperies are often arranged in stripes parallel to the bottom edge, creating patterns that resemble folded fabric. Different colored bands might represent different seasons or different water sources, and in some spectacular examples, the bands create rainbow-like patterns of white, yellow, orange, and brown. Some draperies, called bacon strips by cavers for obvious reasons, show alternating bands of white and red or orange, the colors created by varying amounts of iron oxide in the depositing water. Cave shields, or palettes, are particularly mysterious formations. These are circular or oval formations that project from cave walls like shields, often oriented vertically or at an angle to the wall. They consist of two parallel sheets of calcite with a narrow gap between them, and they can grow to impressive sizes, sometimes several feet in diameter. The mechanism of their formation isn't completely understood, but it's believed that water under hydrostatic pressure is forced between the two sheets, depositing calcite and gradually expanding the formation outward. Helictites represent perhaps the most puzzling of cave formations. Unlike stalactites, which hang straight down due to gravity, helictites twist and turn in seemingly impossible directions. They might grow horizontally or upward, or in spiraling curves. Some look like clusters of worms, others like delicate threads or antlers. The formations can be incredibly intricate, with branches splitting and rejoining, creating three-dimensional sculptures of astonishing complexity. The mechanism behind helictite formation has been debated by cave scientists for decades. The prevailing theory is that they grow through capillary action, with water moving through tiny central channels in the formation, not by dripping, but by being drawn through the formation itself. This capillary flow, combined with variations in crystal growth rates and possibly influenced by air currents or impurities in the water, can cause the formation to grow in directions that seem to defy gravity. Helictites are rare and are considered among the most delicate of all cave formations. Cave popcorn or coralloids are formations that look exactly as their names suggest. Bumpy, knobby surfaces that cover cave walls, ceilings, or floors like clusters of popcorn or coral. These form through a different mechanism than drip-based formations. They're created by water seeping through the rock and evaporating on the surface, or by water slowly oozing out of the rock face rather than by drips. The calcium carbonate precipitates in small knobs and bumps, building up over time to create textured surfaces that can extend for yards across a cave wall. All of these formations, from the simple elegance of a column to the bewildering complexity of a helictite field, are created by the same basic process: water carrying dissolved minerals into a cave and precipitating those minerals as solid stone. But the infinite variations in water flow, drip rate, mineral content, temperature, and cave geometry create an almost unlimited variety of forms. Each cave is unique, each formation chamber a separate work of art. Each individual stalactite or stalagmite a one-of-a-kind sculpture created by nature's patient hand. While the vast majority of stalactites and stalagmites are formed from calcium carbonate in limestone caves, this is not the only material or the only environment in which such formations occur. The same basic principle of precipitation from solution applies in other contexts, creating formations that range from the nearly identical to the utterly alien. Lava stalactites and stalagmites form in lava tubes, the tunnels left behind when molten lava drains away from a volcanic eruption. These formations are fundamentally different from their limestone cousins, yet they share enough superficial similarities that the terminology has been borrowed. In a lava tube, during or shortly after the eruption, molten lava can drip from the ceiling. As it falls and cools in the air, it solidifies, creating pendant formations that hang like icicles of stone. These lava stalactites, sometimes called lava cycles, can form remarkably quickly by geological standards. While a limestone stalactite takes thousands of years to grow even a few inches, a lava stalactite can form in hours or days. The molten rock drips, cools, and solidifies, and with each drip, the formation extends a bit longer. They tend to be irregular in shape, often looking like stretched taffy or twisted rope, reflecting the fluid behavior of the molten material. Lava stalagmites form on the tube floor, where the dripping lava lands and accumulates. Like their limestone counterparts, they tend to be broader and more massive than the stalactites above them, though they're also stubby and irregular, shaped by the viscous nature of cooling lava. In some lava tubes, lava stalactites and stalagmites can meet to form columns, though this is rarer than in limestone caves because the process happens so quickly that conditions often change before the formations can meet. One crucial difference between lava and limestone formations is permanence. Once the lava stops flowing, lava stalactites and stalagmites stop growing immediately and permanently. They won't grow back if broken. In contrast, limestone formations continue to grow as long as water continues to drip, and even a broken stalactite can eventually be covered by new growth, though the break line often remains visible. Ice stalactites and stalagmites, better known as icicles, form in caves in cold climates or at high elevations. These are temporary formations, present only when temperatures are below freezing. Water seeping into a cave freezes as it drips, creating hanging formations of ice. Unlike limestone stalactites, which are hollow when they first form, ice stalactites are usually solid throughout, though they can develop internal channels if water continues to flow through them as they grow. Ice stalagmites, less commonly called by their more familiar surface name, form where dripping water accumulates and freezes on the cave floor. They can grow quite rapidly during cold periods, building up several inches or even feet in a matter of days. The process is essentially the opposite of limestone formation. Instead of minerals precipitating from water, water itself becomes the solid material. Interestingly, ice stalagmites are more common than ice stalactites in caves. This is because warm air rises, so cave ceilings tend to be warmer than cave floors. The ceiling might be just above freezing, while the floor is below freezing, allowing water to drip as a liquid, but freeze when it hits the ground. This temperature stratification creates conditions favorable for stalagmite growth, but not stalactite growth. Gypsum formations occur in caves where the bedrock contains this mineral, which is calcium sulfate. Gypsum stalactites and stalagmites form through the same basic process as calcite formations, but gypsum has different properties. It's softer than calcite and more soluble in water, so gypsum formations tend to be more delicate and more susceptible to damage. Gypsum can also form unusual structures, including the spectacular gypsum flowers, curling, petal-like formations that grow from cave walls, where gypsum-rich water seeps through and evaporates. Cave gypsum can be pure white, creating formations of remarkable beauty, or it can be colored by impurities. Some gypsum formations are translucent, almost glass-like in appearance. In caves in arid regions, gypsum formations can be more common than calcite, creating underground chambers filled with delicate white structures that look like alien gardens. Aragonite, a polymorph of calcium carbonate with a different crystal structure than calcite, can form its own distinctive stalactites and stalagmites. Aragonite formations often have a more delicate, needle-like structure than calcite formations. They can form spectacular arrays of thin, white crystals that radiate outward from cave surfaces, creating formations that look like clusters of frost or crystalline flowers. Aragonite is less stable than calcite over long time periods and tends to convert to calcite eventually. But while it persists, it creates some of the most beautiful and delicate formations in caves. Aragonite stalagmites often grow in tall, slender towers with pointed tops, quite different from the more rounded forms typical of calcite. The crystal structure of aragonite gives these formations a distinctive appearance even to the casual observer. Moonmilk is a soft, paste-like cave deposit that can occur in association with stalactites and stalagmites. It's composed of various minerals, primarily calcite, but with a distinctive texture created by the presence of bacterial communities. Moonmilk formations often appear white or cream-colored, with a consistency somewhat like cottage cheese or wet clay. While not strictly stalactites or stalagmites themselves, moonmilk can coat these formations or form in areas where water seeps through rock walls. In some unusual cave environments, stalactite and stalagmite-like formations can be composed of even more exotic minerals. In mines and artificial caves, formations have been found made of copper minerals, lead minerals, and even opal. These reflect the specific chemistry of water in these environments, but they follow the same basic formation principles as their limestone cave cousins. Perhaps the most unusual category of formations are calthemites, the stalactites and stalagmites that form on and under concrete structures. These aren't natural in the strictest sense, being dependent on human-made materials, but they demonstrate that the formation process can occur anywhere conditions are right. Concrete contains calcium oxide, which reacts with water to form calcium anhydroxide. This calcium hydroxide can then react with carbon dioxide in the air to form calcium carbonate, the same mineral that makes up limestone stalactites. Calthemites can grow remarkably quickly, much faster than natural stalactites. Under bridges, in underground parking structures, in tunnels, anywhere that water seeps through concrete, you might find these formations. Some can grow several millimeters per day under ideal conditions, compared to the millimeter per decade or slower pace of many natural stalactites. This rapid growth is due to the different chemistry involved. The concrete provides a ready source of calcium in a form that's easily converted to carbonate. Calthemites are often colored by the materials in the concrete. Iron from rebar can create orange or red formations. Copper from pipes can add green or blue tints. These formations are considered by some to be a new phenomenon in Earth's history, one that wouldn't exist without human activity. They're also of interest to scientists studying cave formation, as their rapid growth allows observation of processes that would take centuries or millennia in natural caves. The diversity of materials and environments in which stalactite and stalagmite-like formations can occur underscores the fundamental nature of the process. Whenever a solution carrying dissolved minerals enters an environment where those minerals can precipitate, formations will begin to grow. Whether it's calcium carbonate in a limestone cave, frozen water in a cold cavern, molten rock in a lava tube, or calcium leached from concrete, the result is structures that hang from above or rise from below, each one a testament to the transformative power of repeated, patient action. Understanding how fast stalactites and stalagmites grow and how scientists determine their age opens a window into the vast scales of time involved in their formation. These formations are among the slowest growing structures on Earth, yet they can also be among the most precisely dated, making them invaluable tools for understanding our planet's past. The average growth rate for limestone stalactites is remarkably slow, about 0.13 millimeters per year. To put this in perspective, that's roughly 1/8 the thickness of a dime per year, or about 1 inch every 200 years. A stalactite 1 foot long at this average rate would be nearly 3,000 years old. A 6-foot stalactite would have begun forming around the time the last ice age was ending, when humans were still living in small hunter-gatherer bands and agriculture hadn't yet been invented. But this is just an average. Growth rates can vary enormously depending on conditions. In very wet caves with highly mineralized water and optimal drip rates, stalactites can grow much faster, up to 3 millimeters per year in exceptional cases. This is still glacially slow by human standards, but it's fast enough that meaningful growth might be observable over a human lifetime. A stalactite growing at this rapid pace would still take more than 300 years to grow a single foot, but it would reach 6 feet in less than 2,000 years. At the other extreme, some stalactites in very dry caves, or in caves where conditions are marginal, might grow at rates of just 0.01 millimeters per year, or even slower. At this pace, it would take 10,000 years to grow a single inch. These ultra-slow growing formations are often found in fossil passages, parts of the cave system that were formed when water tables were higher, but are now largely dry, with only occasional seepage providing the minimal water needed for any growth at all. Growth rates also vary over time for individual formations. A stalactite might grow rapidly during a wet climatic period when water is abundant, then slow dramatically or stop entirely during a drought. These variations in growth rate are preserved in the formation's structure. Periods of rapid growth often produce layers that are thicker and composed of larger crystals. Periods of slow growth create thin, fine-grained layers. Complete hiatuses in growth might be marked by dissolution surfaces, thin zones where the formation was actually eroded by acidic water before growth resumed. Some of the most spectacular stalactites in the world have had their growth rates studied in detail. In the caves of the English Dales, including Ingleborough Cave and Gaping Gill, researchers have found formations that have been growing for remarkable spans of time. Some stalactites in the fossil passages of Gaping Gill have been dated to at least 350,000 years old. These formations began during the Middle Pleistocene, a time when Europe was experiencing cycles of glacial and interglacial periods, when early humans were just beginning to master the use of fire and complex tools. Stalagmites generally grow at rates similar to stalactites, though there's often significant variation. Because stalagmites receive water that has already passed over or through a stalactite above, they might grow more slowly if much of the calcium carbonate has already been deposited on the stalactite. Conversely, if water drips so quickly that little precipitates on the ceiling, stalagmites might grow faster than stalactites. The interplay between these two processes creates the distinctive pairings we see in many caves. The record holders for size give us some sense of the timescales involved. The world's tallest known stalagmite is in Son Doong Cave in Vietnam, rising an incredible 80 meters, or more than 260 feet, from the cave floor. This massive formation, dubbed the Hand of Dog, has been growing for hundreds of thousands of years. The world's longest stalactite, measuring 28 meters, or about 92 feet, is in Gruta do Janelão in Brazil. These giants have endured through countless human civilizations, through ice ages and warm periods, standing silent witness to the slow turning of geological time. Determining the precise age of stalactites and stalagmites is one of the triumphs of modern geological science. The primary method used is uranium-thorium dating, also known as uranium series dating. This technique takes advantage of the radioactive decay of uranium isotopes naturally present in the calcium carbonate. When calcium carbonate precipitates from water to form a stalactite or stalagmite, it incorporates small amounts of uranium that was dissolved in the water. Uranium is soluble in water, so it can be present in the drip water in trace amounts. Thorium, on the other hand, is not soluble, and so is not incorporated into the forming calcite. This creates a starting condition where there's uranium, but essentially no thorium in the newly formed calcite. Over time, the uranium atoms decay radioactively, transforming through a series of intermediate steps into thorium. By measuring the ratio of uranium to thorium in a sample of the formation, scientists can calculate how long the decay process has been occurring, which tells them how long ago that layer of calcite was deposited. This method can date formations from a few years old to over 500,000 years old, with remarkable precision. The beauty of uranium-thorium dating is that it can be applied to specific layers within a formation. By drilling tiny samples from different depths in a stalagmite, scientists can create a timeline showing when each layer formed. This allows them to calculate not just the overall age of the formation, but also how the growth rate varied over time. A stalagmite several feet tall might yield dozens of dates, creating a detailed growth curve spanning tens or hundreds of thousands of years. Other dating methods can be applied to cave formations as well. Radiocarbon dating, the technique famously used to date organic remains like wood or bone, can be applied to the organic matter that's often incorporated into formations. However, this method is limited to formations less than about 50,000 years old, as that's the practical limit of radiocarbon dating. Annual growth layers in some formations provide another dating method, similar to counting tree rings. In caves where there's a strong seasonal variation in drip rate or water chemistry, formations can develop visible annual layers. These might appear as alternating bands of different colors or textures, with each pair of bands representing 1 year. By counting these bands backwards from the present, scientists can construct precise chronologies. This method, called layer counting or annual band counting, works best in stalagmites from caves in temperate climates where there are strong seasonal contrasts. A wet season might produce thick, clear calcite layers, while a dry season produces thin, organic, rich brown layers. Or winter layers might be chemically distinct from summer layers, due to differences in soil processes above the cave. The precision achievable with annual layer counting is remarkable. In some cases, individual years can be identified going back several thousand years, creating chronologies that rival or exceed tree ring records. One stalagmite from Germany provided an annual record going back over 2,000 years, capturing events like volcanic eruptions and climate fluctuations with year-by-year resolution. Some formations have been dated using multiple methods, allowing scientists to check the accuracy of each technique. When uranium-thorium dates match ages derived from layer counting, or when radiocarbon dates align with other methods, it provides confidence in the results. This multi-method approach has shown that, when properly applied, these dating techniques are remarkably reliable. The ages revealed by these methods are often astonishing. Many formations that seem relatively modest in size turn out to be hundreds of thousands of years old. A stalagmite, 3 feet tall, might have been growing since long before modern humans existed as a species. A 6-foot column might have witnessed the rise and fall of dozens of ice ages. These formations were here before the pyramids were built, before agriculture was invented, before humans learned to work metal or fire clay. They're among the oldest continuously growing structures on Earth. But they're not the oldest. Some exceptional formations have been dated to over 1 million years. These ancient structures formed during the Pleistocene epoch, when the Earth's climate was dominated by glacial cycles, when many modern species were just evolving, when the geography of continents was noticeably different from today. They've been growing through the entire span of human evolution, silent witnesses to our species' emergence and spread across the planet. Perhaps the most scientifically valuable aspect of stalactites and stalagmites is their role as natural climate archives. These formations record information about past environmental conditions with a precision and longevity that few other natural archives can match. Understanding how they do this and what they tell us opens a window into Earth's climatic past that extends back hundreds of thousands of years. The key to stalagmites as climate proxies lies in their growth mechanism. Remember that each layer of calcite is deposited from water that fell as rain on the surface, percolated through soil and rock, and dripped into the cave. This water carries chemical signatures of the conditions it experienced on that journey, and these signatures are preserved in the calcite. One of the most important climate indicators in stalagmites is the ratio of oxygen isotopes. Oxygen exists in several stable forms called isotopes, with oxygen-16 being the most common and oxygen-18 being slightly heavier. Water molecules containing oxygen-18 are fractionally heavier than those containing oxygen-16, and this affects how they behave in the water cycle. When seawater evaporates, the lighter water molecules, those with oxygen-16, evaporate slightly more easily than the heavier ones, those with oxygen-18. This means that water vapor in the atmosphere is slightly depleted in oxygen-18 compared to ocean water. When this vapor condenses and falls as rain, the heavier water molecules with oxygen-18 tend to condense and fall out first, while the lighter molecules with oxygen-16 stay in the vapor longer. The result is that the oxygen isotope ratio in rainfall varies with temperature and with the distance the air mass has traveled from its moisture source. Cold conditions and high latitudes tend to produce rain that's depleted in oxygen-18, while warm conditions and proximity to the ocean produce rain that's enriched in oxygen-18. When this rainwater becomes part of a stalagmite, it preserves this isotopic signature. By analyzing the oxygen isotope ratio in successive layers of a stalagmite, scientists can reconstruct a history of temperature and precipitation patterns. A shift toward more oxygen-18 might indicate warmer conditions or a change in moisture sources. A shift toward less oxygen-18 might indicate cooling or increased distance from the ocean. These shifts can be tracked with remarkable precision through time. Carbon isotopes provide additional climate information. The ratio of carbon-13 to carbon-12 in stalagmite calcite reflects conditions in the soil above the cave. During wet periods when vegetation is abundant, more organic carbon from plant matter is incorporated into the soil, and this organic carbon has a distinctive isotopic signature. During dry periods, there's less vegetation and less organic input. These variations are recorded in the carbon isotope ratio of the stalagmite. Trace elements in stalagmites provide yet another layer of climate information. Elements like magnesium, strontium, barium, and uranium are incorporated into calcite in ratios that depend on various factors, including rainfall amount, evaporation rates, and the rate of water flow through the karst system above the cave. Periods of drought might show increased concentrations of these trace elements as water spends more time in the rock and becomes more concentrated. Wet periods might show decreased concentrations as water moves more quickly through the system. The growth rate itself is a climate indicator. During wet periods, more water drips into the cave, providing more calcium carbonate for growth, and stalagmites often grow faster. During dry periods, reduced water flow means slower growth. By measuring the thickness of annual layers, or by dating multiple points along a stalagmite's length, scientists can reconstruct a history of wet and dry periods. Fluid inclusions, tiny bubbles of the original water trapped inside the growing calcite, provide yet another source of information. These microscopic water droplets can be analyzed for their isotopic composition, for dissolved gases they contain, even for the types of microorganisms present. They're like tiny time capsules, preserving actual samples of ancient precipitation. The combination of all these indicators, what scientists call a multi-proxy approach, provides remarkably detailed climate reconstructions. A single stalagmite might yield information about temperature, rainfall amount, seasonality of precipitation, vegetation cover, atmospheric circulation patterns, even the frequency of storms or droughts. This information can be resolved to annual or even seasonal scale in some cases, creating climate records of astonishing detail. Recent studies have demonstrated the power of this approach. Stalagmites from caves in China have provided records of the East Asian monsoon, extending back over hundreds of thousands of years, showing how this critical weather pattern has varied with changes in Earth's orbit and with glacial cycles. These records have revealed that the monsoon weakened during ice ages and strengthened during warm periods, affecting rainfall patterns across a region home to billions of people today. Stalagmites from Europe have captured the climate fluctuations associated with Dunsgaard-Oeschger events, rapid climate changes during the last ice age that saw temperatures in Greenland swing by as much as 15 degrees Celsius in just a few decades. These stalagmites show that these rapid changes weren't limited to the Arctic. They affected climate patterns across the entire northern hemisphere, altering rainfall in the Mediterranean, changing vegetation in Central Europe, and influencing ocean circulation in the North Atlantic. A study of stalagmites from the Fertile Crescent, the region of the Middle East where agriculture first developed, has revealed how climate affected early human civilizations. Analysis of a stalagmite from Kurdistan showed that the Younger Dryas, a period of abrupt cooling that occurred about 12,000 years ago, brought severe drought to the region. This finding helps explain why the development of farming in the eastern part of the Fertile Crescent lagged behind the western part. The climate in the east was simply too unstable and harsh during this critical period. Stalagmites from tropical regions have provided insights into El Niño events, the periodic warming of the Pacific Ocean that affects weather patterns globally. By analyzing stalagmites from Peru, Indonesia, and other tropical locations, scientists have reconstructed the history of El Niño over thousands of years. These records show that El Niño has not been constant. It was weaker or less frequent during certain periods and stronger during others. Understanding this natural variability helps us better predict how El Niño might change in response to future climate warming. In North America, stalagmites from caves in the Rocky Mountains have revealed the history of drought in the western United States over the past 6,000 years. These records show that the region has experienced megadroughts in the past, dry periods lasting decades or even centuries, far longer and more severe than anything in the historical record. The most recent megadrought ended only about 500 years ago. These findings have critical implications for water management in a region that's already water-stressed. Stalagmites have even captured the signatures of volcanic eruptions. When a major volcanic eruption occurs, it can inject massive amounts of sulfur dioxide into the stratosphere, where it forms tiny sulfate particles that reflect sunlight and cool the planet temporarily. This cooling shows up in stalagmite records as brief periods of altered growth rate or changed isotopic composition. The eruption of Tambora in Indonesia in 1815, which led to the famous Year Without a Summer in 1816, has been identified in stalagmites from Europe and Asia. The North Atlantic Oscillation, a major pattern of atmospheric pressure variation that affects winter weather across Europe and eastern North America, has been reconstructed from stalagmites going back 11,000 years. These records show that the NAO was different during the early part of the Holocene, the current geological epoch. This has implications for understanding how the NAO might respond to climate change in the future. One of the most exciting applications of stalagmite climate records is their use in testing and validating climate models. Climate models, the computer simulations that scientists use to project future climate change, need to be tested against past conditions to verify that they work correctly. Stalagmite records provide precisely dated, high-resolution climate data that can be compared to model outputs. When models successfully reproduce the climate variations recorded in stalagmites, it increases confidence in their projections of future climate. The precision and longevity of stalagmite climate records make them particularly valuable for understanding climate on timescales ranging from years to hundreds of thousands of years. They fill a critical gap between shorter-term records like tree rings and ice cores, which typically extend back only thousands of years, and longer-term records from ocean sediments, which span millions of years but often lack the fine detail and precise dating of stalagmites. Around the world, certain caves have become famous for their spectacular displays of stalactites, stalagmites, and related formations. These caves attract millions of visitors annually and have become important sites for both scientific research and public education about geological processes. Son Dung Cave in Vietnam's Phong Nha Ke Bang National Park holds multiple records and has captured global imagination since its discovery by the world at large in 2009. This cave is not just notable for being one of the world's largest cave passages, with chambers so vast they could fit entire city blocks, but also for containing the world's tallest known stalagmite. This formation, called the Hand of Dog, rises more than 80 meters or 260 feet from the cave floor, taller than most office buildings. To stand at its base and look up is to comprehend, perhaps for the first time, the true scale on which geological processes can operate. The cave's size means that sections of its roof have collapsed, allowing tropical sunlight to penetrate and creating ecosystems underground, complete with their own miniature jungles. Stalactites hang from ceiling sections that remain intact, some of them dozens of feet long. The cave represents one of the most spectacular displays of cave formations anywhere on Earth, a testament to the power of water to create on a truly monumental scale. Gruta do Janelão in Minas Gerais, Brazil, contains what many consider to be the world's longest stalactite, measuring an impressive 28 meters or about 92 feet in length, though competing claims exist from other caves. This formation, hanging from the cave ceiling, like some petrified tentacle, represents hundreds of thousands of years of continuous growth. The cave system it inhabits is part of a larger network that includes some of the most extensive underground river systems in South America. all carved through ancient limestone by the patient work of flowing water. Carlsbad Caverns in New Mexico represents one of North America's most famous cave systems. The Big Room in Carlsbad is one of the largest cave chambers in the world, and it's decorated with countless stalactites, stalagmites, and columns. Some formations here have grown to such massive proportions that early explorers gave them names like the Giant Dome and the Temple of the Sun. The Rock of Ages, a towering stalagmite, has become one of the park's most photographed features. Carlsbad's formations display the warm yellows and oranges characteristic of iron-stained calcite, creating a visual warmth that contrasts with the cool cave air. Mammoth Cave in Kentucky holds the title of world's longest known cave system, with over 285 miles of surveyed passages and counting, as new sections continue to be discovered. While Mammoth is more famous for its horizontal extent than for spectacular formations, it does contain numerous areas decorated with stalactites and stalagmites. The cave's name comes from its mammoth size, not from the extinct elephants, though both the cave and the animals share a name derived from an old term meaning huge or enormous. Parts of Mammoth Cave are actively forming even today, while other sections are fossil passages where formation growth has largely ceased. Jewel Cave in South Dakota is the world's third longest cave, with over 150 miles of passages and still being mapped, and it's known for the calcite crystals that line its walls, giving them a jeweled appearance that inspired the cave's name. The stalactites and stalagmites here are often smaller and more delicate than in other famous caves, but they're accompanied by other formations, including calcite rafts, boxwork, and rare formations called cave balloons, hollow, bulbous features composed of thin layers of calcite. The Eisriesenwelt in Austria is the world's largest ice cave, stretching over 40 kilometers into a mountain. Here, instead of limestone stalactites and stalagmites, formations are made of ice. These ice formations can grow to impressive sizes during winter, when cold air enters the cave, only to melt partially during summer. The result is a constantly changing gallery of ice sculptures, ephemeral compared to their stone counterparts, but no less beautiful. In Ingleborough Cave and White Scar Cave in England, visitors can see some of Europe's most accessible formations. The Sword of Damocles, a magnificent stalactite several feet long, the Buddha and the coffee pot are just a few of the named formations that have attracted attention for centuries. These caves were among the first to be systematically explored and studied, and they played important roles in the development of cave science or speleology. The age of formations in the connected gaping gill system, some extending back at least 350,000 years, speaks to the stability of the British climate over long time periods. Lechuguilla Cave in New Mexico, part of the Carlsbad Caverns complex but separate from the main cave, is renowned for its pristine condition and rare formations. Until 1986, Lechuguilla was thought to be a minor cave, but the discovery of passages extending far beyond the known sections revealed one of the world's deepest and most spectacular caves. The formations here include chandeliers of gypsum, forests of helictites, and stalagmites displaying unusual shapes and compositions. Because the cave has been carefully protected since its discovery, with access strictly controlled, it remains in nearly pristine condition, providing scientists with a laboratory for studying cave processes. The caves of the Dales region in England, including Gaping Gill and the Long Churn system, contain formations that have been dated to remarkable ages. Some stalactites in these caves have been growing for at least 350,000 years, making them among the oldest formations accessible to researchers. These caves have been instrumental in developing dating techniques and in understanding how formations record climate change. Reed Flute Cave in China has been attracting visitors for over 1,000 years, as evidenced by inscriptions dating back to the Tang dynasty. The cave is filled with stalactites, stalagmites, and stone pillars of various colors, created by the different minerals in the limestone. The cave has been artificially lit since the 1960s, with colored lights highlighting the formations and creating a magical atmosphere that has made it one of China's most visited attractions. Waitomo Caves in New Zealand are famous not just for their formations, but for their glowworms, larvae of a fungus gnat that create bioluminescent displays on cave ceilings. The stalactites here exist alongside these living lights, creating a surreal experience where stone and life intertwine. The formations show the characteristic colors of limestone deposits, whites and creams with occasional warmer tones. Shkotsian Caves in Slovenia are a UNESCO World Heritage Site, featuring massive chambers and an underground river. The stalactites and stalagmites here grow in an environment affected by the river, creating formations that differ from those in drier caves. Some are actively washed by spray from the river, creating unusual surface textures and growth patterns. Kango Caves in South Africa display formations in a variety of colors, from white to brown to red, reflecting the diverse geology of the region. The cave system extends for several miles and includes chambers, with names like Van Zel's Hall, filled with columns that seem almost designed to support the massive ceiling above. These famous caves represent just a tiny fraction of the world's cave systems, but they've played outsized roles in public education and scientific research. They demonstrate the diversity of cave formations, from the delicate soda straws of temperate caves to the massive stalagmites of tropical systems, from the colorful deposits of mineral-rich environments to the pure white calcite of filtered waters. Each cave is unique, a product of its specific geology, climate, and hydrological conditions, yet all share the common thread of formation through the patient deposition of minerals from dripping water. The same features that make stalactites and stalagmites so remarkable also make them incredibly vulnerable to damage. Understanding the fragility of these formations and the impacts that humans can have on caves is crucial for their preservation. The most obvious threat to cave formations is physical damage. Stalactites, especially soda straws, can be broken by a touch. Even massive stalagmites can be damaged by impact. In the early days of cave exploration, before conservation ethics were well established, formations were often broken off by souvenir hunters. The most accessible and spectacular formations from many caves were removed and taken to private collections or museums. In some cases, entire chambers were stripped of their decorations. This historical plundering has left many caves with bare walls, where formations once grew, silent testimony to past thoughtlessness. In Ingleborough Cave, early visitors in the 19th and early 20th centuries removed many of the most accessible formations. What remains today, particularly the larger, less accessible formations, survives largely because it was too difficult or dangerous to reach. The finest formations now lie in the deepest recesses of the cave, requiring technical climbing skills to access, which has inadvertently protected them. Even touching formations without breaking them can cause significant damage. Human hands carry oils from skin, dirt, and other contaminants. When these are transferred to a formation, they can alter the surface chemistry where water deposits calcite. The oils change the surface tension, affecting how water spreads and where calcite is deposited. A single fingerprint on a growing stalactite might redirect growth, creating an irregularity that will be visible for thousands of years. In extreme cases, touching can stop growth entirely in that location. The oils can also create dark stains on the white or cream-colored calcite, permanent marks that disfigure the formation. In popular tourist caves, formations within reach of pathways often show obvious discoloration from decades or centuries of handling, a dark patina that speaks to countless casual touches by people who perhaps didn't realize the lasting impact of their momentary contact. Modern cave management has implemented strict rules prohibiting touching formations. In show caves open to tourists, barriers keep visitors at a safe distance. Signs explain why formations shouldn't be touched. Cave guides reinforce these messages, educating visitors about the vulnerability of these natural sculptures. In many caves, these conservation efforts have been successful, with new growth beginning to cover old damage and pristine formations remaining unspoiled. But physical contact isn't the only human impact on cave formations. Changes to the cave environment can also affect growth. Artificial lighting, installed for tourist access, generates heat, which can alter temperature and humidity in the cave. Some lighting systems have encouraged the growth of algae on formations, creating green stains that wouldn't occur in natural darkness. Modern cave lighting uses LED technology that generates less heat and can be filtered to wavelengths that don't promote algae growth. But many older caves still contend with lighting-related issues. The carbon dioxide concentration in cave air is crucial for formation growth. In natural caves, this is determined by the balance between carbon dioxide entering from soil air and rock, and the rate at which cave air exchanges with surface air. When large numbers of visitors enter a cave, they exhale carbon dioxide, temporarily raising its concentration. If this happens repeatedly, with tour groups passing through regularly, the average carbon dioxide level in the cave can increase. This might seem beneficial for formation growth, as more carbon dioxide should mean more carbonic acid and more dissolution of limestone. But the effect is actually opposite. Higher carbon dioxide in cave air means that less carbon dioxide will dégage from drip water, which means less calcium carbonate will precipitate. In extreme cases, high carbon dioxide levels can cause formations to stop growing or even to begin dissolving. Some heavily visited caves have implemented limits on visitor numbers and required ventilation periods between tours to prevent this problem. Water quality affects formation growth as well. Changes to land use above a cave can alter the chemistry of water seeping through the rock. Urban development might increase the amount of pollutants reaching groundwater. Agricultural activities might add fertilizers, pesticides, or increased sedimentation. These contaminants can change the chemistry of drip water, affecting the purity and color of formations that grow from it, or in severe cases, stopping growth altogether. Climate change presents a more insidious threat. Changes in rainfall patterns, temperature, and vegetation cover above caves could all affect formation growth. A region experiencing increased drought might see reduced water flow into caves, potentially slowing or stopping formation growth. Changes in temperature could affect carbon dioxide production in soils, altering the acidity of percolating water. Some caves might see increased formation growth if warming leads to more rainfall and more vigorous soil processes. Others might experience decreased growth or even erosion of existing formations. The specific impacts would likely vary considerably from region to region. The vulnerability of formations to damage has led to the development of cave conservation ethics among cavers and speleologists. The basic principle is, take nothing but pictures, leave nothing but carefully placed footprints. This means not touching formations, not removing anything from the cave, not leaving trash or other materials, and being extremely careful about where you step and place your hands. Many caves popular with recreational cavers have established trails marked with colored tape or reflectors, designed to route traffic away from sensitive areas. Scientific study of formations also requires care. Removing samples for dating or analysis causes permanent damage, as the material removed will never regrow. Scientists must balance their need for samples against the importance of preserving formations. Modern techniques allow useful data to be extracted from very small samples, sometimes just a few grams, minimizing the impact. Drilling is done carefully, often in locations where the hole will be hidden from casual view. The information gained from these samples is considered to justify the small amount of damage, but the decision to sample is never made lightly. Some formations are so valuable scientifically that access to them is heavily restricted. Caves containing particularly important climate records might be closed to recreational caving entirely, with access granted only to researchers with specific scientific objectives. This helps ensure that these irreplaceable archives remain available for future study as techniques improve and new questions arise. The concept of cave wilderness has emerged in some regions, identifying caves or cave passages that should be kept in as natural a state as possible, with minimal human impact. These caves might have no trails, no lighting, no regular tours. They're preserved as examples of what caves are like without human alteration, and they serve as controls for studying the effects of human activity in more developed caves. Education plays a crucial role in conservation. Many people simply don't understand how vulnerable cave formations are, or how long they take to grow. A broken stalactite might take tens of thousands of years to regrow, if it regrows at all. A fingerprint lasts essentially forever on a geological timescale. When visitors understand these facts, they're much more likely to be careful and respectful. Cave rescue and management organizations work to monitor cave conditions and to mitigate damage. They conduct regular inspections of popular caves, documenting formation growth or damage, monitoring environmental conditions, and identifying threats. In some cases, they've closed caves temporarily or permanently when damage from human activity became too severe, allowing recovery time before reopening with better management practices. The legal status of caves varies by country and region, but many jurisdictions have laws protecting significant caves and their contents. Vandalism of cave formations can carry serious penalties in some places, including substantial fines and even jail time for egregious cases. These legal protections reflect recognition of caves as valuable natural and scientific resources that warrant protection. While we've focused primarily on the geological and chemical processes that create stalactites and stalagmites, these formations don't exist in a sterile, lifeless environment. Caves harbor unique ecosystems, and microscopic life plays surprising roles in formation processes. Recent research has revealed that bacteria are far more important to cave chemistry than previously understood. Bacterial communities colonize cave surfaces, including the surfaces of growing formations. These bacteria aren't passive residents. They actively participate in chemical processes that affect calcite deposition. Certain bacteria can catalyze the precipitation of calcium carbonate from solution. They do this through their metabolic processes, which can change the local pH of the water, create nucleation sites for crystal growth, or remove carbon dioxide from solution, all of which encourage calcite precipitation. Some studies have found that rates of calcite precipitation can be significantly enhanced in the presence of certain bacterial species. The first material precipitated from drip water is sometimes amorphous calcium carbonate rather than crystalline calcite. This amorphous form is unstable and gradually converts to calcite, but during its existence, it can be stabilized by bacterial films. The bacteria essentially hold the amorphous calcium carbonate in place long enough for it to begin its transformation to crystalline form, affecting where and how calcite is deposited. Bacterial communities in caves are often found in biofilms, thin layers of microorganisms attached to surfaces and embedded in a matrix of substances they secrete. These biofilms can cover the surfaces of forming stalactites and stalagmites, creating a microenvironment that's chemically distinct from the surrounding cave air or water. The bacteria in these films respire, consuming organic matter and producing carbon dioxide, creating tiny pockets of altered chemistry that can influence crystal growth at microscopic scales. Some cave formations, particularly moonmilk, appear to be heavily influenced by bacterial activity. Moonmilk is a soft, paste-like deposit that can be white or cream-colored, with a consistency somewhere between cottage cheese and clay. It's composed primarily of calcite, but with a distinctive structure that researchers believe may be created by the presence of bacterial filaments. The bacteria appear to provide a scaffold on which calcite crystals grow, creating a texture unlike normal cave calcite. The role of bacteria in cave processes has implications for understanding formation mechanisms. If bacteria are enhancing calcite precipitation, then factors that affect bacterial populations, such as the amount of organic matter in drip water or changes in cave temperature, might affect formation growth rates in ways not predicted by purely chemical models. This is an active area of research, with scientists working to understand exactly how significant bacterial effects are relative to purely chemical processes. Bacteria in caves also play roles in other aspects of cave ecology. They break down organic matter that enters the cave, converting it into forms usable by other organisms. In some caves, bacterial communities form the base of the food web, supporting populations of small invertebrates that in turn support larger cave-adapted species. These ecosystems, called troglobitic communities, are composed of species that live their entire lives in caves and have evolved remarkable adaptations to the dark environment. The presence of life in caves isn't limited to microscopic organisms. Many caves harbor bats, which roost in chambers during the day and emerge at night to feed. Bat guano accumulating on cave floors provides nutrients that support extensive bacterial communities, which in turn support communities of insects and other invertebrates. The chemistry of water percolating through guano deposits is altered by the organic matter, affecting the color and composition of formations that grow in or near bat roosting areas. Some cave-adapted species are found nowhere else on Earth. These unique creatures, often blind and colorless, having lost these features through evolution in the constant darkness, are of great interest to evolutionary biologists. The presence of these species adds another dimension to the importance of cave conservation. Protecting caves isn't just about preserving geological formations, but also about protecting unique ecosystems and species that exist nowhere else. In a few spectacular cases, entire ecosystems exist deep underground, completely cut off from the surface. These chemosynthetic ecosystems, discovered in caves in places like Romania's Mobile Cave, are powered not by photosynthesis, but by chemical reactions, primarily the oxidation of hydrogen sulfide. Bacteria convert the chemical energy into forms usable by other organisms, supporting communities of invertebrates that have been isolated from the surface world for millions of years. While not directly related to stalactite and stalagmite formation, These ecosystems demonstrate the remarkable diversity of life that can exist in cave environments. The study of cave biology has revealed that far from being sterile rock chambers, caves are dynamic environments where geology and biology interact in complex ways. The formations we admire are not just products of chemistry and physics, but also, in some cases, products of biological processes. This intersection of disciplines, geomicrobiology, represents a frontier of scientific research, revealing connections between the living and mineral worlds that were previously unrecognized. As we emerge from our journey through the underground world of stalactites and stalagmites, what perhaps strikes us most is the incredible patience these formations represent. In our modern world of instant communication and rapid change, where we measure events in seconds and accomplishments in days, the timescales of cave formation offer a profound perspective on the nature of change itself. A stalactite, growing at the typical rate of a fraction of a millimeter per year, has no concept of hurry, no deadline to meet. It simply continues its patient accumulation of calcite, drop by drop, century after century, millennium after millennium, building structure through the endless repetition of infinitesimally small acts. This is change at its most fundamental level, not dramatic, not sudden, but inexorable, the kind of change that builds mountains and carves canyons, that transforms landscapes and reshapes continents. The formations we see in caves today began their existence long before human civilization emerged. Many were ancient when the first cities were built, when agriculture was invented, when our ancestors first learned to control fire. They've witnessed the entire span of human history from their silent chambers beneath the earth, and they'll continue growing long after our current societies have become historical footnotes, as long as water continues to drip and minerals continue to precipitate. Yet for all their antiquity, stalactites and stalagmites are not fossils, not relics of a dead past. They're living processes, still active, still changing, still growing. The same drops of water that created the formations we marvel at today continue to fall in, caves around the world, adding new layers to ancient structures, beginning new formations that might one day rival the giants of today. In this sense, every cave is a work in progress, a sculpture that's never finished, always evolving. The scientific value of these formations continues to grow as our analytical techniques improve. Methods that were impossible a few decades ago now allow us to extract information from formations with incredible precision. Annual layers that were invisible to earlier researchers can now be resolved and counted. Chemical signatures that went undetected can now be measured and interpreted. Each technical advance opens new possibilities for understanding past climate, past environments, past conditions on Earth. But beyond their scientific value, stalactites and stalagmites offer something else: a sense of wonder and a connection to processes far larger than ourselves. To stand in a cave surrounded by these formations, to see them hanging like frozen icicles or rising like stone trees, to understand that you're looking at structures hundreds of thousands of years old that are still growing, even as you watch, creates a profound sense of perspective. Our human concerns, so immediate and pressing in the moment, become smaller when set against the patient timescales of geological change. This perspective is valuable, perhaps now more than ever. We live in a time of rapid environmental change, when human activities are altering the planet at unprecedented rates. Understanding how Earth's climate has changed naturally in the past, how ecosystems have responded to those changes, how stable conditions can shift into new states, all of this knowledge helps us navigate our current challenges. Stalagmites provide crucial pieces of this understanding, archives of past change that inform our projections of future change. The fragility of cave formations reminds us of the delicate balance between durability and vulnerability that characterizes so much of the natural world. These formations have endured for millennia, surviving ice ages and warm periods, droughts and floods. Yet a single careless moment from a human hand can destroy what thousands of years created. This serves as a metaphor for our relationship with nature more broadly. Systems that are robust on their own timescales can be remarkably vulnerable to human impacts occurring on our much shorter timescales. Protecting caves and their formations is a responsibility we bear to future generations. The formations growing today will be studied by scientists centuries from now, using techniques we can't yet imagine, answering questions we haven't yet thought to ask. By preserving these natural archives, we ensure that future researchers will have access to the same records of Earth's past that we study today, plus the additional record of our own era, written in the calcite being deposited right now. The study of stalactites and stalagmites bridges multiple disciplines: geology, chemistry, climatology, ecology, even archaeology and history. These formations have been subjects of human wonder for as long as humans have explored caves. Ancient peoples left art and artifacts in caves, sometimes using formations as natural sculptures around which to build ritual or domestic spaces. Modern science has transformed our understanding of these formations from mysterious curiosities into valuable scientific tools, but the sense of wonder they inspire remains unchanged. As we consider the future, we might ask what these formations will record about our era. The isotopes and elements being incorporated into growing formations today carry signatures of our industrial civilization. Slight changes in atmospheric composition from fossil fuel burning, traces of modern pollutants, alterations in rainfall patterns from changing climate. These signals will be preserved in the calcite, future evidence of this pivotal moment in Earth's history when one species gained the ability to influence the planet's systems on a global scale. The slow drip of mineral-rich water continues in caves around the world, as it has for millions of years, as it will for millions of years to come, assuming caves remain and water continues to flow. Each drop adds its tiny contribution to structures that embody patience, persistence, and the transformative power of small actions repeated over vast spans of time. In a world that often celebrates the quick and the spectacular, stalactites and stalagmites stand as monuments to the profound changes that can emerge from processes that are slow, steady, and nearly invisible in the moment. So the next time you find yourself in a cave, or see images of these remarkable formations, take a moment to appreciate not just their beauty, but what they represent. Each one is a testament to time itself, a three-dimensional timeline written in stone, a sculpture created by the simplest of processes, the patient accumulation of minerals from drops of water, repeated billions upon billions of times across millennia. They remind us that profound transformations don't always come from dramatic events, but sometimes emerge from the steady, patient work of simple processes acting over inconceivably long periods. And if you enjoyed this journey into the underground world of cave formations, if you found yourself marveling at the patience of water and the artistry of chemistry, if you're left with a deeper appreciation for these silent sculptors beneath our feet, then consider subscribing to this channel. There are countless more wonders in the natural world waiting to be explored. From the microscopic to the cosmic, from the quick to the geological. Each one offers its own lessons about the nature of our planet and our place on it. Hit that like button if you'd like to see more deep dives into the science and history behind Earth's most fascinating phenomena. Until next time, remember, the most profound changes often happen so slowly that we can't perceive them in the moment. But given enough time, drops of water can create cathedrals of stone,